In this lecture, we will discuss the space of continuous functions. This is the set of all continuous functions between two topological spaces considered as a topological space on its own. So, for this purpose, suppose that x and y are topological spaces, and we denote by cxy. This is the set of all continuous functions from x to y. So this is the set of functions from x to y. F is a function. So notice that this space of the set of all continuous functions from x to y, it is the subset of the set of all functions which I denote f and xy. This is the set of all functions from x to y. However, this is nothing but the product space indexed over the domain, which is x, and the family of topological spaces which I denote by yx. So here yx equals y for all x, which means that each yx is taken to be y with the same topology that we are starting out with. So this f and xy is just another notation for the arbitrary Cartesian product, and this is the set of all functions from x to y, whether they are continuous or not, and the set of all continuous functions lies inside this bigger space. And we are going to consider two topologies. So two topologies on this set. So we are going to put two different topologies on this set. One will be coming from the product topology. So here, since this is an arbitrary Cartesian product, we can put the product topology on this space, which only takes into account the topology on y, because for the product topology we don't need any topology on x to define the product topology. However, the other topology, which will be for the special case when y is a metric space, will take into account both topologies on x and y. So first of all, let us start with the product topology on the set of all functions from x to y, and keeping in mind that these are functions, this product topology has a special name. So when x and y are topological spaces, we have a special name for this product topology. So the product topology, so this is just some terminology, and this is that the product topology on the set of all continuous functions from x to y is called the topology of pointwise convergence. So we have a special name. This is the topology of pointwise convergence, and we will see why it is called the topology of pointwise convergence in a moment. But first, let us fix some notations. So an element in the space element f of fn xy. So this is a function, f from x to y. Now we have, since this is the since fn xy is the arbitrary Cartesian product with each yx equal to y, we have the j-tuple notation. Here j is equal to the index set here is x, so j is equal to x. But the j-tuple, in the j-tuple notation, we write any member f as f subscript x, where x ranges over this index set x. So this is the j-tuple notation. Remember when we had x which belong to a Cartesian product of topological spaces x alpha over some index set j, we wrote x as x alpha over j. So this is the j-tuple notation. Here we are writing, don't get confused with the points here which are denoted by x, and points here which are points in the topological space capital X. They are two different things. So let me maybe write x tilde just to avoid confusion. So here we use the j-tuple notation in this fashion, but notice that these are all functions. So we also have the functional notation. So in this notation, f is written as f of x. So this is the usual way to write a function, where the argument of the function is contained within parentheses. So this is the functional notation, and we will only use the functional notation for f and xy. This is because we are viewing them as functions, and it will be especially useful when considering sequences of functions, because if you consider sequences of functions in the j-tuple notation, then there are many subscripts, and we want to avoid that. So we will use the functional notation only. And now let us go back and treat the terminology of topology of pointwise convergence, and why the product topology is called as such. So let us look at a theorem which describes this property. So here is the theorem explaining why the product topology on the set of all functions from x to y is called the topology of pointwise convergence. So for this we consider a sequence of functions fn. So each fn is a function from x to y, and so this sequence is considered in the set of all functions fn x y. And suppose that this converges to a function f from x to y. So this in the notation that we used before for convergence of sequences, fn converges to f, and the topology that we are considering for this convergence is the product topology on fn xy. So a sequence fn of functions converges to another function f in the product topology on fn xy if and only if the sequence yn, which is fn of x for x in x, where x belongs to capital X, in y, because we are using fn, so fn of x lies in y. And for if you consider the collection of points f and x, where x is fixed but n is varying, then you get a sequence in y, and this I have denoted as yn. And this sequence converges to y, which is f of x. So in this notation for the convergence of sequences, we have yn converges to y in the topology of y, which is the same as saying that fxn converges to this is fn of x fn of x converges to fx in y, and this should be for each x in x. So the convergence of sequence of functions in the product topology in fn xy is the same as the convergence of fnx to fx in y for each x in x. So this is why, so this convergence, this is the pointwise convergence part of it. This is the pointwise convergence, because it means that whenever you evaluate or consider the image of a point under the sequence of functions fn, that sequence in y converges to the image of the function f, which the sequence fn converges to at the point x. So this is why this is pointwise convergence. Okay, so let us look at a proof of this theorem. So to start off, suppose that fn converges to f in fn xy in the product topology, and now we have to show that fnx converges to fx in y for each x in the space capital X. And remember that this is equivalent to showing that for each neighborhood v of f of x, there exists a capital N in the natural numbers such that we have that f and x belongs to v for all n greater than or equal to this capital N. And so we have to show this second part here. So given any neighborhood of fx, we want to find a capital N for which f and x belongs to v for all n greater than or equal to capital. So how do we show this? So now consider the open set pi x inverse v. So remember that v is open in y and x contains f of x, and we consider the open set pi x inverse v. So this is open because this is the one of the sub basis elements. So this is the sub basis element for the product topology on fn xy, and here pi x is the, if you want, the coordinate projection map. So this is a map from fn xy to y, where it takes a function, so pi x of f for any function in between x and y, and it is defined as f of x. So it is just the evaluation map at x. So this is the evaluation of f at x. So this is how we define pi x. And remember that this is pi x inverse of v is a sub basis element for the product topology on fn. So this is an open set. And notice also that pi x inverse of v can be described as the set of all functions g in fn xy such that g of x belongs to v. So this is the by definition almost the inverse image of the coordinate projection map pi x. So with this definition, it is clear that f is contained in pi x inverse v, since v f of x is contained in v. So v is an open neighborhood of f of x, of the point fx, and therefore we have f belongs to pi x inverse v. And now we can use the fact that fn converges to f, and this is our starting assumption here, that the sequence fn converges to f in the product topology. And therefore, since fn converges to f in the product topology, so there exists a capital N such that fn belongs to this neighborhood of f, which is given by pi x inverse v in the product topology, for all n greater than or equal to capital N. So this we can get from the convergence of this sequence in the product topology. And this means that fn of x belongs to v for all n greater than or equal to n. And this is what we wanted to show, that there exists a capital N for which fn x belongs to v for all n greater than or equal to n, and this means that fn x converges to fx in y. So we have shown that if you assume that fn converges to f in the product topology, fn x converges to fx for each x. So because we chose our x arbitrarily, so this is true for each x in x. So this proves that fn x converges to fx for each x. And now for the reverse implication, so suppose now that fn x converges to fx for all x in x, and we have to show that fn converges to f in the product topology, which is the same as saying that given any neighborhood u of f, there exists a capital N belonging to the natural numbers such that fn belongs to this neighborhood u for all n greater than or equal to this capital N. So we have to find this capital N using the fact that fn x converges to fx for all x. Now since u is a neighborhood of f, it must contain a basis set which contains f. So since u is a neighborhood of f, there exists a basis set in the product topology so let me call this set w, such that f is contained in w, it is contained inside this open neighborhood u. And now we use the basis, the form of basis sets in the product topology. So w is of the form w is equal to the intersection of finitely many sub-basis sets. So it is of the form pi x1 inverse v1 intersection pi x2 inverse v2 intersection pi x let's write xn inverse, or maybe xm here, xm inverse vm. So it is a finitely many, this is a finite intersection of sub-basis elements in the product topology. So w is of this form, and notice that this implies that vk is a neighborhood of f of xk for all k belonging to this set 1, 2 up to m. So this just means that fxk is contained in vk. So all of these vk's are open sets in y, and W is an intersection of the pre-images of these open sets under the coordinate projection maps pi x k. And so this means that fxk belongs to vk, and so vk is a neighborhood of fxk for each k. And this means since fnx converges to fx for each x, this means that so there exists so for each k, so for each k in the set 1 to up to m, there exists a number nk, a natural number nk, such that fnxk belongs to vk for all n greater than or equal to nk. So we are using the fact that f and x converges to f of x, and of course this choice of this capital N depends on the point xk, or in this case just on the index k. So for each k we have to choose nk, which can be different for different k. And this means that if I take n to be the maximum of these numbers n1, n2 up to nm, then we have that fn belongs to this intersection of all these subbasis sets pi x1 inverse v1 intersection pi x2 inverse v2 up to pi xm inverse vm. And this is simply because fn of xk belongs to vk, and this holds for all n greater than or equal to capital N, which is the maximum of all these numbers n1, n2 up to nm. And this is nothing but the set W. So this is equivalently we can say that fn belongs to W for all n greater than or equal to n, and this is the same as saying that fn converges to f in the product topology. So this is a implication here that fn converges to f in the product topology, and this is what we wanted to show. So we see that the convergence in the product topology is equivalent to convergence of each of these evaluations of the fn's at each point, and fnx then converges to the point f of x for each x. This is why it is called the topology of pointwise convergence. And now we specialize somewhat and we consider another topology on the space of all functions from x to y, but for the case when y is a metric space. So let us see what is the definition of this topology.